Okay, so we are going to start with binary codes. If you think about it, computers is just about zeros and ones, right? Just on and offs. So we have discussed this previously that how a computer work is just really what is the voltage in a transistor? Is it high or is it low? If it's high, that's a one. We say that the state of the transistor is on, or if it's low voltage, then we say it is off. So that is really how computer work. Then we say that that property of a circuit where it can be on and off, we can translate that into binary. So we can represent um, sort of numbers with it, and we have looked at that, converting decimal numbers, hexadecimal numbers, and octal numbers into binary, and vice versa. So we have looked at that. But if you look at it, is this all we need, right? Is numbers all we really need to work with computers? So the answer is definitely not, and we're gonna need more than that. So what about alphabets? What about special characters? What about things like that, right? And then to do that, we will need encoding. Some sort of encoding that will map or translate some binary numbers into some alphabets or some sort of special characters or anything like that. So we have to think about that, and that is really called encoding. So that's what we are looking today. We'll be looking at a couple of them starting with binary coded decimal, that is BCD, then ASCII, and then EBCDIC. And then also Unicode, right? So ASCII and ABCDIC are standards, and we'll talk about it later on. So we'll start with BCD for now. So binary coded decimal, if you think about it, we can convert any number into binary. So for example, we have a number, let's say, for example, 5139, right? So if you remember the process of doing that, how we used to do it, um, we would have to think about this: how big is this number, right? And how many bits would we really need to represent this number, right? So for this number, if I think about it, we definitely need more than one byte, because 8 bits or 1 byte can represent a maximum of 255 numbers, right? So we know that. Okay, so I apologize for my writing. That's because I'm just really typing with my finger. I'm writing with my finger. So anyway, so we definitely need more than 8 bits, more than a byte, and we have to think about that. So that is one way of converting numbers to decimals, right? So let's look at another way of doing it, and that is binary coded decimal. So how we do it is that we convert every decimal digit into an equivalent binary number. Okay, and if we see how many how many decimal numbers we really have, we have a total of 9. So starting with 0 and going till 9. Um, so that's really the total number of decimal numbers we have, which is a total of 10. So we'll have to convert that into binary, and we have done that previously. So a 0 is represented by 4 zeros. Basically just one 0 is also enough, right, to represent 0. uh, um, but to represent all the numbers from 0 to 9, we definitely need uh, at least 4 bits, right? So if you see that in the fourth, in number 9, which is the maximum number that is there in decimal system, to represent number 9 in binary, we need the first and the fourth bit to be on, right? And for that reason, the minimum number of bits that we need is 4. So in binary coded decimal, all we have is 4 bits, and anything that is more than 4 bits, or anything that represents a number that is more than 9 in decimal, right? That is equivalent of more than 9 in decimal, is basically invalid in binary coded decimal. So anything like 1010, so that is representative of the number 10, right, in binary, in decimal, and that would definitely not be something that would be valid. Why? Because so that's in the fourth bit, so it represents the number 8. Okay, so 8, and this is in the second bit, so it represents the number 2. Yeah, because in the second place, so 8 plus 2, that is 10, right? And 10 is not found in decimal, right? As a base number, so the total we just go from 0 to 9. So that is why all these numbers are not valid BCD numbers, right? They are invalid. So that is something we need to be aware of. Okay, so let's look at an example. This will make it pretty clear that what are we talking about. So let's say we have to convert 2709 into binary coded decimal. So we will have to, how will do it is basically we will start from the left hand side and we will convert every digit of the decimal number into binary one by one. So we start with 2. 2 is converted into binary like that. So the first bit of the number represents the number 1 because it's 2 to the power 0, right? That's the first position. Then the second bit represents 2 to the power of 2. Sorry, 2 to the power 0 and then 2 to the power 1. So 2 to the power 1 would just basically mean 2. So this is equivalent of 2. Similarly, we're going to convert the rest of them as well. So 7, we have to turn the first 3 bits on, right? The first bit represents 1, the second bit represents 2. We have a total of 3 now. And then the third bit represents, 4. So 4 and 3, we have a decimal number of 7. Yeah, so 2 and 7, that's what we have done so far. Then we move on, 0, that's pretty straightforward, all bits are off, and then 9, so 1, 0, 0, 1, right? The eighth uh, uh, bit and the first bit, right? So 8 plus 1 is 9. So this is really how you convert a number from decimal to binary. Just a recap that remember what this 10 means here, right? This 10 would really mean that we are trying to say that this number is a decimal number. We write the base of that number system in the subscript. So in this case, it's going to be 10. So moving on, that is how we really converted it to 2709 is equal to this number. So just one more thing to remember, we definitely need to have some sort of space, right, or some sort of separator between this, and that is very important, right? So if you think about it, if we don't do that, this could easily be mistaken as um, a number of 16 bits, right? So we have total of 16 numbers, so that's 16 bit. So it could easily be mistaken, and that would be a problem. So we would want to have some sort of separator here, and secondly, we would also want to write BCD in the subscript. So both of these will help to identify that this is really a binary coded decimal number. So we have to make sure that we do that, both of them, write a BCD and also have some sort of separator. Sometimes a dot also perfectly works between the separate digits. So now let's look at another example. Ideally in the class I would get you guys to do this, but it's okay, I'm going to do it now. So binary coded decimal, if I have a number 1 2 3, so this would be the equivalent of it in binary, right? So that's 1 2 and 3, right? So what I'm going to do is that I'm just going to simply write it, so all three with some sort of separator, right? And there you go. So I have just converted this decimal number into binary coded decimal. This should be pretty clear to you by now how I converted these three decimal numbers into binary. We have done that. Okay. So now let's look at the difference between binary coded decimal BCD and binary, right? Because it should be pretty clear to us by now. Um, so let's say I'm trying to represent the same number, which is 123, in binary as well. So I'm just going to recap the process of basically converting a decimal number into binary. So I'm going to do that now. So I'm starting with 123. The first thing I want to think about is that how many bits do I need, right? So as I said, we usually start with a byte, right? We move on the sets of byte, so that means 8 bits, right? So I can think about it in this way. Let's start with 8. So an eighth bit in binary is really translate to the decimal number of 128, right? So I'm going to think, can my number 128 go into uh, the number I'm trying to represent? Can 128 go into 123? So definitely it cannot, because 128 is more than 123. So that means I will not need the eighth bit, right? So I can sort of either write 0 in the place of eighth bit, turning it off, or I can also just totally get rid of 0. So I'm not even storing the eighth bit with me. So I'm just working with 7 bits, right? So that's a bit better, because now my memory is saved. I don't even need the eighth bit. So that is why in this case we are trying to represent it with 7 bits. And why 7 bits? We will think about it in this way. So 128, we can discard that because it's more than our number. What is the number which translates to the seventh bit? The seventh bit would be equal to, in decimal, of 64. So half of 128, 64, right? So can 64 go into 123? So indeed it can, right? So that means the seventh bit, which is right here, right? The seventh bit, I will need to uh, turn that on. I will need to make it a 1, right? So I know I have 64 already. So I have represented 64 already, right? I'm done with 64. So once I'm done with 64, I need to subtract that 64 from my number, because I don't need to worry about 64 anymore, because I've just turned the seventh bit on, which represents 64. So 123 minus 64 would be equal to 59. So that means I still have to worry about, and I still have to really deal with 59. Okay, so I still have to deal with 59. So now I have to think about this. What is the sixth bit, right? Sixth bit would also mean the next bit from the seventh bit. So that would be half of 64, which means it will be 32, right? So I'm gonna think, can 32 go into 59? This is the question I'm asking. And sure enough, it can, right? So that means I will have to turn the sixth bit on as well. And that is what I've done here. Yeah. Um, but I need to find out what else I have to deal with. So I'm going to subtract the 32. I'm done with 32, so I'm going to subtract it from 59. I still have 27 left, right? So I have to deal with that. So I'm going to move on. I'm going to move on to the next bit in line, which is the fifth bit, right? And fifth bit is represented by 16, right? So you are basically making your number half every time. Okay, so now I have to see if 16 can go into my remaining number, which is 27, right? So sure enough, it can. So I will turn the third bit on as well, right? And now I'm going to subtract it, because I'm done with 16. So I'm going to subtract it, and now I have 11 to deal with, right? And 11, okay? The next bit, which is 8, right? I will need to turn that on as well, okay? Following the same pattern. So 11 minus 8, 3. So I have to turn so I have to deal with 3 at this point, right? But my next bit seems it is not something less than 3, it is more than 3, because it is 4. So if I divide 8 by 2, right, take a half of it, that will be 4. So 4 cannot go um, into 3, right? So that means I will have to keep the third bit, which is this one, off, right? So 4 cannot go into 3, right? So the third bit would be off, right? But I still have to deal with 3. The next bit in line is 2, right? So 2 can, right? So I have to turn that on, and then I'm still left with 1, right? So I'm gonna have to turn the first bit on as well. So that's the 1. So what I really got is this number, yeah. So 4 times 1, then 0, and 2 times 1. Okay, so the same number, which is 123, okay, it's just a bit hidden there, but it's there. 123 is equal to this number, really. Okay, All right, so we move on to the next example. Um, so let's take this example now. We have a number here. So you might have this kind of questions in the quiz or in the exams. So we have been given a number, a BCD number. How do we know it's BCD number? Because we have separators here. In this case, it's a space. It can be dot as well, right? So we have been given a BCD number, and we have to convert that into a decimal number. So just like we were converting each number separately from decimal to BCD, we're going to do the same thing here, right? So we can start from right hand side or left hand side, really, it doesn't matter. But let's start from left hand side, right? So what is this number really? So in this number, it's a 4-bit number. Definitely it has to be 4-bit number in order to be BCD. So we have the first bit on and the third bit on, right? The first bit represents 1, the third bit represents 4. So 4 and 1, 5, right? So this bit represents 5, right? So I'm going to write it here. Yeah. Then I'm going to look at the second one, that is really 1 and with 3 zeros, right? So the fourth bit represents 8. So that's all it is, because none of the other bits are on, right? So that's 8. So 5 and 8, right? Similarly, I'm gonna check this. So that's the 2 and 4, right? So 2 and 4 equals to 6. So I have 6, and this is just the first bit is on, so that's a 1, right? So I'm gonna write it 5, 8, 6, 1. So this is how you really convert from BCD to decimal. Okay. Also, we need to think that how many bits we would need, right? How many of these pieces would we need? So it's really simple. For example, if we need to represent 99 in BCD, right? So now we have two uh, decimal numbers. So we would definitely need 8 bits, right? We would need 8 bits, because for a set of 4 bits would represent one number, right? So that's why we would need a total of 8 bits, because we have two decimal numbers, right? That is why we needed a total of 16 bits, right? 16 bits in this case to represent this number, because we had 4 digits. Yeah, we had 4 digits, so that's why we needed 16 bits. So this is how we really do it. So with 8 bits, what is the maximum number we can represent, right? And for that, you have to remember the formula. What it was? It was base, right, uh, to the power of n minus 1, right? So this was really the formula. The base in our case is 2, so 2 to the power of n minus 1, right? With this simple formula, you can easily find what is the maximum number you can represent with this number of bits, right? You can write it here. So n number of bits. So we can always find it there. Okay, so now to compare binary and BCD once again, right? And how we find the maximum numbers they can represent. Let's look at this here. So in binary, if I have 8 bits, right, and I turn all of them on, so the maximum that I can do is 255, right? We already talked about it. So if I take a 2, right, and take a power of 8, that would be equal to 256, yeah? But remember, we are subtracting 1 from it, right? In the formula, we're subtracting 1 from it. And since we are doing that, we would be left with 255. So why are we really subtracting 1 from it? We are doing that because we started with 0. We didn't start with 1, right? So we started with 0, and that is why we now have to subtract that 1 from it. So we are left with 255. So that is what we are representing here. Um, in the same scenario, if we have 8 bits in binary coded decimal, the maximum number we can represent with it is 99, because we really deal with sets of 4 at a time. So the first 4 bit at the maximum can represent 99, sorry, a 9. Why it can do that? Because if I turn one more bit on, it is no longer a valid binary coded decimal number, right? The maximum it can be in this configuration 1009, sorry, 1001. In the similar way, if we have a 4-bit number, 4-bit number in binary. So if we turn all of the bits on, we will have 15. Yeah. Why would we have 15? If you look at the formula and we put 2 to the power 4, right? So that would give us 16, but then we have to subtract 1 from it. So we would be left with 15. But in the case of BCD, binary coded decimal, this is the maximum we can go, right? As as soon as you turn any other bit on, right? I just turned the third bit on, right? This is not a valid binary coded decimal number because the maximum number we can represent is 9. Okay, so this is really all about binary coded decimal. We have a couple of examples I'll be giving to you guys. So please practice that because that's the only way you are going to fully understand it and you're going to remember it long term. So please do that, and we're going to move on to